So today we're going to review some basics of dynamics that we need for the fundamentals that we will use on vehicle safety and crash reconstruction techniques. This is the review of the kinematics of particles, which talks about motion, basically how things move. Um, we have a situation where you see there is a particle that goes from point O to P and travels through a distance x. You can have either a rectilinear motion if they travel a straight line, or you could have a curvilinear motion depending on the path that it follows. What is important is to realize that in crash reconstruction, the position of objects is important, and that's where I want to start here. Now, so we use a scale to map a scene, or just a Cartesian plane to be able to determine where each point and it's at each position. Okay. Uh, Basic concept. What is velocity? Velocity of a particle is equal to the rate of change of the position. And we say that the position is a vector, and so the derivative should be also a vector. What does that mean? I think this is small detail. I consider that is an important one, enough for us to just just take a good look at it. Let me see if it's over. I can make notes on here. You see, what I'm trying to say is that if the particle goes from O to P, the vector position really is like this, see? So the magnitude of x, which normally we put this, in this case would be the number of units of the display, so 1, 2, 3, 4, 5, 6, 7, let's say 8, yeah? And the direction, you could say alpha would be, if we measure alpha to be an angle which one point is in regards to another one. At some degrees, let's say 10 degrees. See? So you see what I mean? What I'm trying to say is that the vector has the use amount, or you could say, yeah, the length, it would be a good term to me. But this other one is the direction. The direction. Vectors always, you could say vectors have these two components, or you may say these two characteristics, yeah. Yeah. So whenever we go like this, and we say v is dx dt, when I was a student, I remember my professor, he always liked to put it like this. And I thought it was very funny notation that he used, but everything he did was like that. And he put like the acceleration vector like this too, like this. Yeah? I didn't think it was that important, but I think over the years, particularly teaching students to become engineers, and these are basic things that need to be well cemented in your mind. And the point is that whenever you specify a velocity, let's say a departure velocity, two vehicles collide, and you're going to specify a departure velocity, it's going to have these two components. So whatever we do, whether it's a position, velocity, or acceleration, we are dealing with vectors. And dealing with vectors means that it will have a magnitude and a direction. The acceleration is the rate of change of the velocity vector. So velocity, rate of change of position; acceleration, rate of change of velocity. There's one more thing though. Do you know what the rate of change of the acceleration is? How's that called?
Jerk.
Yeah, it's called jerk. And in this case, it becomes important because some devices and some vehicles measure the change of acceleration. Okay, and you're gonna get data that, especially from the EDR, in some models that say that, hey, this is jerk, and you'll have to do some spreadsheet in Excel to do the integration to get the acceleration. To do another integration, you get the velocity, another integration to do the position. Okay, which is in fact what working model 2D is doing. You know, when you go to the menu and you say measure, and it says velocity, measure position, and so on, you don't you we don't see it because the computer puts the numbers, but magically they don't happen. It has to be with some quantity and that is measured or a sense, and from then on is can do the calculations for the other. So these are some of the ways to express the acceleration. In some instances, it may become handy, although most we don't use this form. ASB times dVdx is the same thing as d square x dt squared. See, I think this one is much easier to remember. That one, this one. Look at the difference here. A positive value of v, the velocity, indicates that the particle moves in the positive direction, and a negative value moves in the negative direction. Huh? Positive value of a might mean that the particle is truly moving faster, let's say, in the positive, or that it is decelerated, moves more slowly in the negative direction. So this is the case with cars, because if you go to a stop sign and you're gonna stop, you're still going towards the stop sign, but the acceleration is working against the direction of the travel. That's why in this case acceleration is negative. Whenever the car is decelerating, slowing down, the acceleration is always negative. Okay. And then we go to the equations of motion for different kinds of motions in here. The first one is that the velocity of a particle in uniform rectilinear motion is that the position is the original position plus the distance traveled when the particle had a velocity. That means that the total position x is going to be x0 plus velocity times time. Now it comes to the three equations that all of us must know. And when we take U110, your professor also tells you you have to remember this equation. Now we better have them, I remember them in our sleep. We have to know these three equations because they act independently, and they are very helpful to find the the main variables: velocity, position, and acceleration, and time. Actually, we have those four, and a combination of those. So there might be occasions where the unknown is the final velocity. Other occasions, the unknown is the initial velocity. In another occasions, there might be the time, might be the question. So if you have x is equals to x0 plus vt, this is uniform rectilinear motion, no acceleration. That's what the first one is. However, if there is an acceleration, the velocity, I usually like to write final velocity. Like here I say final velocity is the initial velocity times at. So this is the 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 most elementary one. The velocity, the final velocity is equal to the initial velocity plus whatever change of that velocity happened. Okay, and then the other one is that the position is the initial position plus the v sub 0 t, which is the initial velocity times time, and then plus 1/2 of at squared. This is the typical equation that we find in parabolic motion. In this case, well, of course, this holds also true for rectilinear motion, where you have an initial velocity and acceleration. The acceleration is the rate of change, say the amount of change of the velocity in each second. So if I say 9.81 meters per second squared, it means the velocity is going to change on the first second is going to be 1, and in the next is, so each second is going to increment by 9.81. Okay, so that is the case. So there's the position. Then the other one is the velocity final square is v sub 0 squared plus 2ax. So meaning the velocity final is velocity of the center of mass, well, it's not the center of mass of initial velocity, plus 2ax, x being the difference in the position, okay? We also can locate the position of one particle with respect to the position of the other. Like in this case, we can say that the position of B is the position of A plus the position of B with respect to A. So that notation x b slash A means the position of the point B with respect to A. So A is our reference point. So when particles A and B moves along the same straight line, the relative motion of B with respect to A can be considered. So you say denoting that the x, the position of B with respect to A, is the relative position of B with respect to A. We have x of B is x of A plus x of B with respect to A. And then if you differentiate this with respect to t, you have that with respect to time, that the velocity of the point B is the velocity of A plus the velocity of B with respect to A. By the same token, the acceleration of a point B is the acceleration of A plus the acceleration of B with respect to A. Okay, let's take a look at these problems and also to look in the and use the graphical approach in here. So in this case, the solution involves the position and time and the velocity time and the acceleration time curves. This is true too for crash reconstruction because they're gonna ask you to map out as time went on how the vehicles move, because what happens is that after a collision one car may slide and then go back and finally stop. Yeah. So it's important to keep track as and to explain the marks on the road, whatever, from the crash. You see, if you have a plot of the acceleration and time at a given time, you could say the velocity 2 minus velocity 1, so the change in velocity is the integral of t1 and t2 at. That is, in fact, that's where the first equation of motion comes in, because if you integrate this, you're saying that the change in velocity is equal to the acceleration times time. So what is interesting on these graphs is that you are able to see the change of the velocity on the blue line, uh, in the green light and the change of the position in the blue light. Now, this is going to be important because vehicles don't travel in straight lines. They travel in curvilinear lines. And so we have to look as to how the concepts hold in there. Would it still be true that the velocity change of the position, but could we express it in terms of the vector r? In other words, the position of the point P of this point depends on the position of this and where this is going. Okay, so in this case, the path is from P0 to P, and it travels some arc, but you have the position vector r is the position vector with respect to an inertial frame. Inertial frame meaning a frame that does not move. Okay, so the velocity vector is tangent to the path of the particle and has a magnitude b equals to the time derivative of the length s. Right. So the velocity vector is tangent to the path of the particle and has a magnitude equal to the derivative of the length So in here also, you could define the position of a, a particle by looking at the change of the vector. See here, this is the original position. You have this the change in P. Okay. All right. So this is the velocity is dr dt, and the acceleration, of course, dv dt. This is going to give you a more of a graphical representation of how things change. Like in this case, the velocity is the change of the position with respect to time, right? And in this case, the acceleration of the acceleration of a particle not necessarily is tangent to the path of the particle. Is actually defined by the relationship dv dt. But I already told you that when you talk about dv dt, it's got to involve the direction and the magnitude. Okay, let's take a look at the position, velocity, and acceleration as we define the unit vectors for 3 dimensions. But you begin to see that, this little cube could be represented an entire vehicle. See? when you look at the 2K110, you didn't have that vision, but it's perfect for this class because you can see here how you define the position of a vehicle with respect to an inertial frame. You have the position P on the body, and then you have the values of each one of the coordinates that determine the inclination of the vector R. So if you put the rectangular coordinates, and then we plot the rectangular components of the velocity and acceleration, okay, so you have this unit vectors, and you have the R vector which positions on the the center of the object here. But you see that this could be the center of mass of this body. Okay. So we have that the velocity in the x direction is x dot. The velocity in the y direction is y dot. And the velocity in the z direction is z dot. And same thing is true. You differentiate the acceleration in the x and the y and the z respectively. Okay. This is another thing that I would like to review is that you can attach a frame to the point A and let the point B vary. So you see here there is the red frame, which we're going to call it a rotating frame, or translating, depending on what the application is. So if you look at it in terms of vectors, the position of the point P, that RB, is the position of A plus the rate of change from A to B. This is very helpful. And it holds to all three variables. For the position, you say the radius A plus the other radius R with respect to A. Okay, so we have that equation for the velocity as well as the same equation for the acceleration. It's important to understand what it means. See here. Yeah. Great. So we could in here for the rotational do a normal and tangential acceleration. And in here you have that the acceleration in here is the yeah. So we need to see which variables we are being asking here, and then you have that the it's another way of writing the the acceleration equations in terms of the unit vectors. E1 is the vector in the tangential direction, and En is in the, yeah, one is in the perpendicular direction and the other one is towards the point. So in this case, for a particle, we say, okay, we put the unit vectors so that we can actually decompose it into the components, and in fact that's what has happened here. In the velocity and accelerations are in terms of the tangential and normal components. You could do like the tangential component, have dv dt or p dot in there, and the other one is going to be controlled by the normal acceleration. Okay, so we have in here particle dv dt. This is written in terms of the tangential and normal coordinates. So in this case, in this equation, b is the speed and the particle, and p is the radius of curvature of its path. So the velocity is directed along the tangent to the path, and the acceleration vector consists of a component A directed, along the tangential direction, which is b alpha t, and then the other one is the normal acceleration. Okay. This is another way of representing things. It's called polar coordinates. And in doing mechanics of rigid bodies, many times local polar coordinates save us a lot of time. And here you have the polar coordinates are theta and r. Remember I told you we need, for each vector, we need that, and it's convenient to use radial and transverse component directed respectively along the position vector r of the particle and the direction combined by rotating x through 90 degrees. So we put unit vectors in the r direction and in the normal direction. And you can have a little different interpretation of the equations in polar coordinate, but because they're written in terms of E and E sub 0. Then this is a picture more of the acceleration vector, the tangential acceleration and the normal acceleration. And here there is if you're using those two components, ER and E theta, this is another way to write the equations of motion by knowing the acceleration of each. Okay, So now there you have it. For a curvilinear motion, we can use this system. Any questions about this? So that's pretty much self-explanatory, the basic equations of kinematics. Right. So let's stop now for a moment in the explanation and see if we do an example.